Achieving elegant and efficient geometry in architectural frames with casting technology and advanced manufacturing. Day's End Project Case Study. My name is Jennifer Anna Pazdon, Vice President of Connex. Inspired by an earlier work by Gordon Matta-Clark, Day's End features custom stainless steel castings at each of the frame intersections to accommodate a variety of connection typologies to define the overall geometry of the frame. The compact super-duplex stainless steel castings contribute to the ephemeral expression of the artist's intent, while addressing the technical difficulties associated with the riverside location. Historically, steel castings have been used to manufacture complex connections that define geometry in architecturally exposed applications. Likewise, they have been exploited for the advantages they offer over traditional fabrications in industrial and transportation applications, where high-performance materials and resilient connection designs are necessary to resist very large structural forces and meet both fatigue and corrosion performance requirements. At Day's End, the cast nodes define the geometry of the complex three-dimensional frame while simultaneously accommodating relatively simple circumferential welded connections that offer improved fatigue performance over conventional built-up fabricated connections. Thus, the nodes at Day's End are similar to the industrial castings with respect to their weld details and technical requirements for strength and fatigue, while also being similar to the architecturally exposed castings described before, which feature castings for their aesthetics and geometric freedom. Precision detailing of the cast steel nozzle ends enabled a simple CJP butt groove weld to be used rather than a more complicated TYK tube-to-tube CJP groove weld that may have been used in conventionally fabricated alternative connections. This moved the connection from a stress category DT to a stress category C1 as defined in IASS 360, offering an order of magnitude of improvement in fatigue life. Transition from the beam members to the column members was accomplished within the body of the casting, where smooth, tapering geometry ensures that stress risers are minimized. The offset of the weld away from the face of the column reduced the flexural demand on the weld, as well as the bolted coupler connection. Following advanced finite element analysis and detailed shop drawing production for both as-cast and machine geometries of each node, manufacturing oversight was provided by Connex, including rigorous project-specific QA/QC. Casting manufacturing engineering is coordinated with the foundry with direction from a project-specific production specification. On the left is a recording of a CFD analysis conducted to determine gating and feeding design. On the right, shrinkage and solidification are modeled. Each simulation influences the final design of tooling for optimal continuity of the as-cast part. Tooling is CNC milled from timber. Sand molds created from the timber tooling define the interior and exterior surface of the castings. Molten steel is poured into the molds, with real-time testing to confirm the alloy. Test blocks are created from each pour for destructive testing. After a time, the castings are demolded, sand is shaken off, and quenching and tempering may be performed as per ASTM and/or project specifications. Non-destructive examination, including RT, UT, and MT, are conducted on the as-cast part to meet project-specific acceptance criteria. Machining is performed, here seen on the nozzle ends of the weld preps, and NDE is repeated on the machined parts. Machined parts are thoroughly 3D scanned to confirm geometries are within millimeters of the design intent. Here, fabricated bents await shipping to New York City. Bolted couplers join bents to horizontally spanning members to complete the structure. As a complement to the successful project, conceptual redesign was performed on an example node from the Day's End project to investigate geometric and structural forms that may be possible using advanced design and manufacturing techniques. In this case, topology optimization and metal additive manufacturing, or MAM. Simplified load cases used for the optimization of the conceptual cast steel node were determined by considering a subassembly of the frame and assuming inflection points at the midpoint of the structural members. The ratio between the shear and bending moments were inferred by assuming a simplified lateral load behavior, and the force magnitudes were scaled until any one of the adjoining tubes reached its yield moment. Topology optimization was used as a form-finding process based on simplified loading. Adequacy of the part was subsequently confirmed using the actual load cases for the structure. The optimized part was exported into 3D CAD software, and a final geometry was developed based on the form that was apparent from the top-op analysis. This final topology optimized part was 58% of the mass of the original part. Finite element analyses were subsequently performed on the modified part using the original project-specific load cases. For these analyses, nonlinear material behavior was assumed. The topology-optimized part displays somewhat higher stress values than the original part. Stresses were increased around the tight radii and curves associated with the top-ops part's cutouts, although it is noted that the strains in these regions were quite low, and thus the modified part is expected to perform adequately under the required static loading. The fatigue performance of this updated part would be compromised due to these stress risers as compared to the original cast part, which features smooth, continuous tubular geometry. In this particular project, where connection weight concerns are relatively unimportant compared to the fatigue performance and aesthetic continuity, this modified part would not offer increased value over the original cast part design. However, the interesting geometric form, light weight, and capable structural performance under static loading indicate that such a design process may in fact be desired in other projects, depending on the particular structural and architectural requirements. Casting technology allows for the creation of complex 3D geometry, but the process has limitations in this respect tied to the way that casting molds are created. In contrast, MAM parts may be better suited for the creation of parts like the one optimized before. An investigation of the current state of the MAM industry and how it may be applicable to the structural, architectural, and construction sectors was conducted with the top-op part as a case study for comparison. SLM is a type of powder bed fusion process wherein a laser beam is used to melt the powder at each layer. It's one of the most common forms of MAM that is currently commercially available. Due to its ability to produce high-quality parts, SLM is currently used in the aerospace and automotive industries, and from a quality perspective, is considered to be a viable option for producing metal components suitable for structural applications. Quotations from 2 SLM manufacturers demonstrate the large variance in the price of components in the nascent world of MAM manufacturing, and suggest that MAM part costs remain uncompetitive with casting manufacturing. The following present significant challenges to the future use of structural parts produced with MAM processes, including SLM. Of particular concern when considering MAM part quality control are the touch points, which will likely be machined and must be free of inclusions and other defects that may affect the welding process or compromise the connection performance. Thus, advanced NDE and the ability to perform weld repairs will likely be required in any production MAM part that is used in structural applications, and this is cited as an area of future research that must be addressed before widespread use. Thank you. We look forward to your questions.